Dear students, welcome to the class on analog and digital communication subject. Today we are going to discuss a new topic, that is digital modulation. And in the digital modulation specifically, we will talk about ASK and FSK. So students, in the previous class, we had talked about pulse code modulation in detail. And when we discussed pulse modulation, I told you that pulse modulation lies in between our analog communication and digital communication. In fact, many scientists or experts in the field, they say that your pulse modulation techniques are not actually modulation techniques. They are a kind of representing your signal digitally. Okay. And we have seen that in case of our pulse amplitude modulation, pulse width modulation, pulse position modulation, what we were doing in pulse amplitude modulation, we made our signal discrete in time with the help of sampling. Okay, and then we talked about pulse code modulation, where we introduced discreteness in time as well as in amplitude. But if you remember, when we defined modulation initially, when we started with this subject classes, I told you that we need a carrier. Though we said that the carrier in case of pulse modulation technique was in the form of pulses, but it was not an analog carrier. Okay, so that way we can say that they cannot be full-fledgedly called as modulation technique if we talk in terms of the carrier requirement. Fine. So that's why we have to move to digital modulation technique, where we will again be using sinusoidal carrier, which will be of high frequency in nature. Okay. So before we move further, we need to understand the concept of digital modulation. So as from the name itself, it is clear that in digital modulation, we transmit digital signals. Okay. So digital modulation means carrier is not digital. It is the information signal which is digital. Okay. So your digital modulation is concerned with the transmission of digital data. Okay. Digital data here means the user message that is digital in nature. Fine. So here in digital modulation, we transmit our data in the form of discrete message or in the form of bit streams. And we all have studied pulse code modulation. There, when we transmit bit stream, we have already understood the fact that it has discreteness in time as well as in the amplitude. So in digital modulation, at the message level, if I talk about, our message will be both discrete in time and in the amplitude. Okay. So the main difference is this one only, that our information signal here is of the type digital and we transmit digital data. Okay. So then after we have this digital data, we will be using analog carrier signal to carry that digital data. Okay. So in digital modulation, precisely if I say that here analog carrier signal is modulated by a digital bit stream. Fine. So obviously, since our original information signal is analog in nature, be it your voice signal or your video signal, all are analog in nature. So obviously, if we want to use digital modulation, we need digital message signal or digital information signal. So originally occurring information signal, which is analog in nature, it has to be converted to digital by the use of analog to digital conversion at the transmitter side. And at the receiver side, we need to convert digital signal back to analog original message signal at the output of the receiver side. So here in digital modulation, we will be requiring analog to digital and digital to analog conversion. Okay. So as I told you that we will be using analog carrier signal. So obviously this digital modulation that way is a continuous wave modulation scheme. The signal that goes out of the transmitter, it is of the form continuous wave. I hope all of you have been able to understand this. Your concepts will be further clarified as we look into the detailed block diagram of your digital modulation or digital communication system. So this is what I told you, that the block diagram of digital communication system. So I told you that our original information signal is analog in nature. So whatever signal we get from our information source, that is analog, be it your voice signal or your video signal. So since this is our analog signal, we need to convert this signal into digital signal with the help of A to D converter. Okay, so if you use bipolar signaling, then this will be the kind of thing. And if you use in the form of unipolar pulses, your digital signal will look like this, which is discrete in time as well as in your amplitude. Fine. So with the help of A to D converter, we convert our analog information signal into your digital information signal. Okay, so we will talk about this source encoder and channel encoder just in few minutes. Let me discuss other blocks. So once we have obtained digital information signal or digital data, we use modulator. And this modulator is obviously digital modulation technique modulator, which modulates our digital signal onto the analog carrier. So once we have obtained our digitally modulated signal, we transmit our signal through channel. Then at the receiver side, we have demodulator, which does the reverse of the modulator. Fine. And then again, after demodulation, we get the digital data back, but we want our original information signal back, which was analog in nature. So we need to use D2A converter to convert our digital signal back to the original analog signal. So this is the main crux of your digital communication. And I told you in the previous class as well, and in the initial classes of this subject, that we want to save our bandwidth, we want to save our power. Simultaneously, we also wish that our signal reaches at the receiver side successfully without any distortion. Okay, or with minimum distortion or minimum noise. So here in digital communication system, we have a block that is called source encoder. Since after A to D converter, our signal has been converted to digital domain, we use source encoder to make our signal compact. Okay, so whatever redundancy is present in our digital signal, we remove that redundancy so that our signal becomes compact, and we will be requiring smaller number of bits to transmit our original signal. That is the main job of source encoder. But simultaneously, we have to ensure that compactness doesn't mean that we can compromise with the information. We cannot delete the relevant information, we cannot remove the relevant information. So after we have compressed to the best extent possible, then obviously your signal has to move through channel. We will have to prepare our signal to be transmitted in such a way that whatever distortions are present in the channel, those distortion do not affect my signal significantly. So your channel encoding schemes are there which make my signal robust so that it is able to fight against the distortions in the channel. So our source encoder, it makes my signal compact, it removes redundancy wherever possible, whereas channel encoder makes my signal strong so that my signal is able to counteract the distortions in the channel. Okay, so in channel encoder, we add redundancy. So your source encoder tries to reduce the bit rate, whereas your channel encoder tries to increase the bit rate. So there is a trade-off between the two, and whatever is desirable, we proceed accordingly. So obviously at the receiver side, we will be requiring channel decoder to decode the effect of channel encoding, and then we require a source decoder. So with all these small blocks forming the complete block diagram of digital communication, we can explain the concept of digital modulation techniques. I hope all of you have understood this. If you look at this figure on the left hand side of this slide, it further clarifies our concept of digital communication. So here you can see that I have directly represented my information signal in the form of digital data or in the form of 0 and 1. And you all know that computer is a digital device. So whatever data comes from computer, it is in the form of digital data or it is in the form of ones and zero. So that digital data is passed on to the modulator that modulates digital data onto the analog carrier. Okay, so at the output of the modulator we have analog signal, analog modulated signal. Okay, and the information signal is actually digital in nature. Fine. And then once it reaches demodulator, we again convert this signal which is received from the channel side to our original information signal, which was digital in nature. Okay, so this is how we explain the concept of digital communication or digital modulation technique. I hope all of you have understood this. Next. So students, we want digital everywhere nowadays. Okay, so whatever electronic gadget we buy, we want that digital. Whatever uh, equipment we want, we say that it is digital. Whatever channels we watch on our television, we say that it should be digital. So why at all digital? So we need to understand why digital communication is required. And one reason, we all know that your digital communication systems, they are immune against noise. So one of the biggest advantage of digital communication is the noise immunity. And we have discussed this concept in detail while discussing about PCM, that is pulse code modulation. So same concept applies here, that your digital communication techniques provide improved noise immunity, as a result of which my signal quality is significantly improved. Okay, so apart from noise immunity, another thing that make digital communication technique robust against noise is the concept of regeneration. So I told you in the PCM also that in case of digital communication technique, we can regenerate the pulses. So obviously whenever there is a long distance between transmitter and receiver, so whatever pulses we transmit from one place to another place, because of noise in between these pulses, they get distorted, or the top of the pulses get distorted, or noise enters into our pulses. So regeneration means we will refresh these pulses, means we know what is the level of these pulses. We will remove those noise components which have creeped into my signal, and I'll generate fresh pulses. This is what happens at the regeneration. So I send refreshed pulses when I regenerate. Okay, so in digital communication system, regeneration is possible with the help of repeaters for long distance transmission. That is another important point that helps us in justifying the use of digital communication for long distance transmission. Next. So apart from noise immunity and regeneration, another important advantage of digital communication is that we can mix, we can simultaneously transmit different natured data. Okay, your information signal may be voice, it may be video, it may be some high data rate signal. So these are different kind of signals. With the help of digital communication, it is possible to simultaneously transmit these signals. And why it is so? Whether it is voice or video or your high data rate signals, once they have converted into digital domain, all are in the form of ones and zeros. And once we get those ones and zeros, then it doesn't uh, we are not able to distinguish directly just by looking at it whether those bits belong to voice or video or high data rate signal. So for channel or for the system, digital communication system, these are simply ones and zeros. So we can have simultaneous transmissions. Simultaneously we can group them also together. That is, multiplexing is possible in case of your digital communication technique. So apart from your noise and regeneration, there are other points also which are very, very important that works in the favor of digital communication. Another thing is, since we have ones and zeros, we have discrete signals, we can use some secure transmission techniques, we can use some secure codes or some encryption that gives us highly secure transmission in digital communication. See students, once we have got our signal in the form of zeros and one, then we can apply a whole lot of processing techniques, signal processing techniques, and other techniques to improve the robustness of my signal to be transmitted. Okay, so that was not possible in case of analog, because my analog signal or analog modulation techniques, they were dependent on the waveform which were transmitted. So we were mainly concerned with the shape of the waveform, okay, shape of the signal that we transmitted, whereas these digital signals, they are waveform independent, they are all ones and zeros. Fine. So that way we can apply extra processing, and those extra processing techniques are simple also. And in digital communication, though we are able to use we use number of blocks, it seems that our circuit has become complex, but in entirety your digital communication modulation circuitry is relatively inexpensive because of the use of VLSI techniques. Okay, so these are the main advantages of digital communication which make them suitable for your long distance communication. Fine. Then it's not that digital communication techniques do not offer any disadvantages. We all know, we discussed in PCM also, your digital communication system, they occupy large bandwidth. We require analog to digital conversion and digital to analog conversion. Then another thing I discussed in detail in PCM was the quantization error. Because of quantization, deliberate distortion has been introduced into the signal. So these are a few disadvantages, but keeping in mind the number of advantages that we have as compared to disadvantages, we have digital communication techniques a boon for a communication engineer. Okay, next. So we have different types of digital modulation techniques, as we have talked about in analog communication and your pulse communication. In the same way, we have different types of digital modulation technique. If we obviously in digital modulation also, uh, though our signal is digital in nature, rest of the things are similar to that of your analog modulation technique. So we can change the amplitude of my carrier, you can change the frequency of the uh, carrier, you can change the phase of the carrier depending on your message signal. And since your message signal is in the digital domain, so your message signal can have two or more than two finite discrete states. Obviously your message is in digital domain, so at the minimum side you will have two symbols, either 1 or 0 when you use binary code. So you have two discrete states, and you may have more than two discrete states also. So if you use binary, then you have two discrete states. If you use quaternary, you have four discrete states, and so on. So if the amplitude of the carrier signal is changed in accordance with your digital information signal, we get ASK. So students, here in digital modulation technique, we say amplitude shift keying, as we saw in your amplitude modulation in analog domain. So in ASK, which is equivalent to your AM of analog communication, your amplitude of the carrier signal is varied in accordance with the digital information signal. You must note this word, digital information signal. Next is FSK, where the frequency of the carrier signal is varied in accordance with our digital information signal. That is your frequency shift keying, FSK. Then we have PSK, where the phase of the carrier is varied in accordance with uh, or in proportion to the digital information signal. Okay, and we call that as phase shift keying, that is PSK. Fine. So we have three types of digital modulation techniques: ASK, FSK, and PSK. So we will also look at their waveforms, though these waveforms we have also seen in our lab classes when we discussed ASK, FSK, and PSK there also. So these are the waveforms of digital modulation techniques. So this is our digital information signal in the form of your ones and zeros. So your ones and zeros has been represented in the form of pulses here. Okay. So the duration for which your one is there, we call that as symbol duration. Okay. Or the duration of the bit. Fine. Then in case of your ASK, that is amplitude shift keying, during one your amplitude was 1, your carrier is present. During 0, no carrier present, then carrier present for 1, then carrier absent. This is my ASK. If you multiply your carrier with the amplitude of this baseband signal. Then next in FSK, what we have in FSK, my frequency of the carrier signal is varied in accordance with my digital modulating signal. So here during 0, I'll have one frequency, say F1, and during 1, I'll have another frequency, say F2, and then and so on. So here again F1, then we have F2 here, F1 here, F2 here. So I'll be shifting between two different frequencies when I use binary FSK. Then we have PSK, that is phase shift keying, and here we are using binary phase shift keying, means there will be two phase changes in the PSK signal or of the carrier. So as you change from 0 to 1, uh, obviously we know that the maximum value of our phase angle is 360 degree, and if we use binary, then 360 by 2, that gives us 180. So in case of BPSK or binary PSK, we'll have a phase change of 180 degree as we move from 0 to 1 or 1 to 0. So you can see here, when we move from 0 to 1, there is a phase change of 180 degree. Then again, if we move from 1 to 0, then again we have a phase change of 180 degree. Then again phase change of 180 degree. Then we have the transition from 1 to 0 again, then again there is a phase change. So since phase change of 180 degree means nothing but phase reversal, so that's why your carrier value, carrier signal values, it is reversed in phase. Okay, so this is our phase shift keying. So I hope you have been able to understand these digital modulation techniques waveforms. Next. So we will now talk about ASK and FSK in detail. First, let us talk about amplitude shift keying. As I told you here, the amplitude of my analog carrier wave, my carrier is analog in nature and my information signal is digital in nature. So the amplitude of the carrier is varied in accordance with my information signal. Okay, so this is what I get. So this is my ASK signal. So during 1, my transmitter outputs the carrier, means carrier will be present during 1, and during 0 it will suppress the carrier, means carrier will remain absent during the 0. That's why we call ASK as on off keying. Fine. So mathematically what is happening here, if you multiply 1 and 2, okay, if your bits are represented in the form of ones and zeros, and 1 means say high volt and 0 means 0 volt, if your digital signal is represented in the form of unipolar pulses like this, then if you multiply, you get simply ASK. So mathematically ASK is obtained by the multiplication of your carrier signal and the amplitude of your binary pulses. So for binary 1, you have your output as a cosine of 2 pi fct, and during 0, you'll get the 0. Okay, so this is the concept of ASK. So before we move further, we need to understand one important point here, that what is the difference between symbol and bit. Again and again, since I started with the digital modulation concept, I am saying bit, but I haven't talked about symbol. So actually, we should say that in case of your digital modulation technique, your digital symbols are modulated, okay, with the help, or your carrier is modulated by digital symbols. Okay, what does it mean? That in case of analog signals, we say that my sample values or my signal values are there, whereas in case of your digital signals, we give it a term symbol. Okay, your symbol may have one bit or more than one bit. If you remember, in case of see, uh, we did the quantization process. We also looked into the details of quantization. So there what we did, we represented our each sampled value or each quantization value by a group of bits. So if we use 3 bits for a given quantization level, then your one level was represented, say, with a group of 3 bits, say 011. So this 011 is nothing but a group of bits, and we call it as symbol. Okay, so your digital information signal, depending on how many number of bits are simultaneously representing a given digital symbol, uh, it is decided what kind of that digital modulation technique is. So if your symbol is represented by 1 bit at a time, means if we have 1 bit per symbol, okay, in that case we'll have, say, either 0 or 1. So at the maximum we will have two different symbols, and we have binary modulation technique. If my symbol, each symbol is represented by 2 bits, in that case how many symbols are possible? In that case 4 symbols are possible, where each symbol is represented by 2 bits. Fine. So these 4 symbols then give us quaternary modulation techniques. So your symbol may have 3 bits, your each symbol may be represented by 4 bits. Okay, so that way we should be able to understand this thing, that your we actually represent our digital data in the form of symbols. Okay, and then each symbol is represented by a group of bits. So if each symbol is represented by only 1 bit, in that case your symbol rate is same as that of the bit rate. Okay, otherwise your symbol rate will always be less than bit rate. So generally my symbol rate is always less than or equal to the bit rate. So this concept you should be able to understand, that we always talk about symbols first, and then we talk about the number of bits which are being used to represent a symbol. Fine. So that was the concept of symbol and bit, and the concept of ASK in general. Okay, so now we need to look into how to generate ASK signal and how to demodulate ASK signal. Though we all have talked about amplitude modulation, amplitude demodulation, pulse amplitude demodulation. So if we have discussed those concepts in great detail, then it will be very simple job for us to discuss the modulation and demodulation of ASK. Okay, and the disadvantage that was associated with the AM, that is your noise immunity of AM, was lesser. Similarly in ASK, your noise immunity is not good as compared to FSK and PSK. Okay, but ASK is simpler as compared to your FSK and PSK. Fine. So that analogy exists whenever we talk about your amplitude based modulation techniques. Next. So this is what we have in the generation of ASK signal. I told you that mathematically what we are doing the multiplication of carrier signal and our digital modulating signal. So your ASK is generated by the multiplication of your message signal and carrier signal. And I also told you that during 1 your carrier is present and during 0 your carrier is absent. So if we talk in terms of block diagram or in the circuitry, we need a multiplier. So here my information signal, digital information signal comes, and this is my carrier signal which is generated by the oscillator. And if you multiply, we get your ASK signal. So there is nothing much to explain in it. It is very, very simple to generate ASK signal just by using a multiplier. Next. So then we have ASK demodulation. We discussed two types of demodulation in our your analog demodulation techniques also. I told you that we have two kind of demodulation techniques. One is known as your coherent demodulation and your non-coherent demodulation. So non-coherent demodulation techniques are those techniques where we do not generate carrier at the receiver side. Whatever signal we receive, we use that signal to demodulate our original signal. Okay, so in non-coherent, whatever signal we get from the channel at the input of the receiver side, that is used to detect our signal back. So same is the case here. So your envelope detector that we had in our amplitude demodulation, that was nothing but an example of non-coherent detection. So same thing, same kind of thing we have used here also. So here also we are detecting the envelope. Okay, we are first, see, if you look at these two things carefully, or if you look at the modulated signal of ASK, it is nothing but my information signal is present only in the envelope of this modulated signal. So I need envelope detection. Okay, so here this was my modulated ASK signal. With the help of rectifier, I convert my bipolar signal into unipolar signal. So once I have done that, then I'll be using low pass filter. Okay, so this low pass filter will give me the envelope of the signal. It will allow only low frequency modulating signal to pass through, and your carrier will be removed. Okay, so at the output of low pass filter, what I'll get these levels, these discrete levels for corresponding to my demodulated signal. And if you remember, I had explained you while discussing pulse code modulation concept, and that was the advantage, or uh, that was the advantage of digital modulation technique. And I told you that we are simply concerned with whether my pulse is present or pulse is absent. Okay, so here by looking at the different levels that I get, I'll compare those levels with my threshold levels. Okay, with the help of comparator. So if my value of a given level is more than the threshold level, I'll take that uh, bit or that signal as 1. And if the value of a corresponding level is below threshold, I'll take that as 0. So I'll be using a comparator for comparing my received signal level with the help of predetermined threshold to decide whether 1 or 0 has occurred. So this is how I get back my data signal. Okay, obviously it is not the complete binary ASK detector. We will need to convert my digital signal into analog signal if it was original analog signal. If it was original data signal generated by some computer directly, then this is my nothing but the original data signal. Okay, so here you can see that I have not generated any carrier locally at the receiver side. I am simply using the uh, modulated signal I received from the channel. That's why it is non-coherent binary ASK detection. Okay, and the main advantage of non-coherent demodulation technique is that they are simple, but the disadvantage is that their performance is low as compared to your coherent detection technique. Fine. Next, so now after non-coherent detection, we need to look into coherent detection technique. So here in coherent detection technique, what we have, I told you that we will be using a carrier wave. Okay, so this is a locally generated carrier. Fine. And this locally generated carrier will be processed along with my ASK signal. Fine. So this is the concept of coherent detection or coherent demodulation technique, that I use uh, locally generated carrier. Okay. So students, this is what happens in our coherent demodulation technique. Fine. So what we do, your ASK waveform is multiplied with the locally generated carrier. Okay, we all have seen such kind of thing in our amplitude demodulation also. I'll show this thing to you mathematically also. Then after we do the multiplication, we use a low pass filter, and here you must be observing a block of integrator. Okay, your integrator is nothing but it is a low pass filter. I have explained that thing in earlier classes also. So your integrator is nothing but your low pass filter. So once you have passed your output of multiplier through a low pass filter, then we need to again take a decision whether 1 is present or 0 is present, depending on the value of the threshold value, and I get the demodulated signal back. Okay, so such kind of thing we had also seen in our amplitude demodulation. So mathematically, if we see here, uh, say this carrier wave is represented by uh, vc dash, which is equal to vc dash cosine of omega ct. Fine. Then at the output of the multiplier, what we expect, we expect the multiplication of my ASK signal with my locally generated carrier. And what is my ASK signal? ASK signal is nothing but the multiplication of my uh, message signal and my carrier signal. Okay, so I have cosine of omega ct again. So two cosines are multiplied, means cosine square omega ct. And we know that cosine square omega ct is nothing but equal to 1 plus cos 2 omega ct by 2. So if I do that, I get this expression when my symbol is 1. And in ASK, we already know that we have output as off when my symbol is 0. Okay, so I get when my symbol is 1, S1 equal to Vm Vc Vc dash by 2 into 1 plus cosine of 2 omega Ct. Now you see here, we have two things here. One is the DC component or low frequency component. Another is high frequency cosine of 2 omega Ct. So once you pass this thing through a low pass filter, this twice of omega Ct component is removed. Okay, as a result you get vmvc dash, means your output s2 at the output of integrator is proportional to nothing but your modulating signal. So this is how we are able to demodulate our message signal back. Fine. So this was our coherent binary ASK detection, because we have used locally generated carrier at the receiver side. And as I told you, the performance of your coherent detection technique is 3 dB higher, at least 3 dB higher as compared to your non-coherent technique. but because of this carrier wave presence, my complexity has increased because I need to synchronize this locally generated carrier with the carrier which is present as a part of ASK waveform. So that synchronization part adds the complexity to the signal. Okay. So after we have discussed ASK in detail, now our job is to discuss frequency shift keying, that is FSK. So as I told you, in frequency shift keying, what will happen, whether my signal is 1 or 0, the frequency of my carrier will be shifted. So during 1, I'll have carrier frequency F1 present. During 0, I'll have carrier frequency F2 present. So depending on the change of my uh, modulating signal values, the frequency of my output signal will change, or you can say the frequency of my output signal will shift from one frequency to another frequency. That's why we call it as FSK. So whenever my data bit is 1, then my transmitter outputs high frequency carrier, and when my uh, data bit is 0, my transmitter output is a low frequency carrier. So here you can see that my carrier frequency is shifted in steps, and it is shifted in 2 steps. That means I am using binary frequency shift keying, means my modulation symbol carries, or it is represented with 1 bit at a time. Okay, so that's why I'm calling it as binary FSK. So during binary 1, my output will be the multiplication of my information signal with the corresponding carrier frequency. During 0, my output will be the information signal and the corresponding frequency of the carrier. So mathematically you can see here that for binary 1 my frequency is F1, for binary 0 I have my frequency F2. Okay, so during 1 or 0 my frequency will hop from one frequency to another frequency. This is my frequency shift keying. Now this is how we generate our FSK signal. So this is a simple diagram where you can see that my binary data is in the form of 1 and 0. So during 1, what will happen? My frequency F1, or cosine of 2 pi F1t, will be transmitted at the output. During 0, my another branch will work. So I have used a NOT gate which will activate this branch, and as a result my F2 will be channelized at the output. So in a way you can say that during 1, F1 will be switched at the output. During 0, F2 will be switched at the output. Okay, so we have two multipliers, we have a switch, and we have the adder at the output that gives us FSK signal. So here one very important concept is there that you need to appreciate with regard to generation of FSK signal. You must not have thought of this concept while discussing or while thinking about FSK signal. And that concept is, we have basically two kind of FSK signal. One is called discontinuous phase FSK signal, and another is continuous phase FSK signal. See, the diagram that I'm showing you just in this slide for FSK signal generation, you can see that I have two frequencies. One is F1 and another is F2. And since these are two different frequencies, so obviously the sources of these frequencies or the oscillators of these frequencies are different. Okay, and the frequencies which are generated from two different sources, their phase cannot be matched. If you look at this output FSK signal carefully, then you see continuous signal present. See, this FSK signal seems to be continuous. Okay, but in case of discontinuous phase, or in case these two frequencies F1 and F2 are generated from two different sources, there will be discontinuity in the phase here. You cannot match. Okay, because their phase are their phase cannot be same. because of the generation from two different sources. Like if you have during one some uh, carrier frequency present, and then during zero the frequency that you generate, it may have some phase discontinuity. Say it generates like this. Okay, so some kind of discontinuity is present here. The phase cannot be continuous, and because of this discontinuity in phase, there are so many things or so many problems that come in the transmitted signal at the antenna side, in the amplifier. So because of this discontinuity, so we never advise to go for discontinuous kind of FSK, though theoretically we can say that okay, discontinuous FSK is okay, but practically we do not go for discontinuous FSK. Practically what we go for, we go for continuous phase FSK. Now the question arises that how do we generate continuous phase FSK? So students, it is very very simple. All of us have studied FM, that is frequency modulation. So in FM what we did, we had FM modulator. Okay, at the input of FM modulator what we had analog information signal, and we used high frequency carrier, and we got, or we generated frequency modulated signal. Fine, and its frequency was varying, though like in the diagram I am not able to show or draw clearly your FM signal. But in case of FM, my modulating signal was analog in nature. So if you, instead of analog modulating signal, if you provide digital information signal at the input of FM, the job of FM is whatever is at its input, it has to generate your output signal frequency accordingly. So simply in case of your FM modulator, if you provide your digital information signal, you get continuous phase FSK. Because in case of FM, you have a single carrier whose frequency is varied in accordance with your information signal. Okay, so this is how we generate continuous phase FSK, where there is no phase discontinuity, and we are able to achieve good quality FSK signal which is continuous in phase. Fine. So I hope all of you have understood this generation of FSK signal. Next. So again, the same kind of thing as we discussed in ASK, non-coherent and coherent ASK detection. So we have in FSK also as non-coherent and coherent FSK detection. Okay, so as I told you, in non-coherent, we do not have any locally generated carrier. So we get FSK signal directly. So here, as I told you that in case of FSK, we will have two frequencies. One is F1. Okay, so this is centered around F1 and this is centered around F2. So we use two band pass filter centered around F1 and F2 respectively. Okay, so whatever FSK signal is there, it is combination of these two frequency, because your input point is common. So your FSK signal consists of frequencies corresponding to both 1 and 0. So both 1 and 0 will go to band pass filter 2, where F2 components will be passed and F1 will be rejected. Here F1 components will be passed and others will be rejected. Okay, so once we pass my FSK signal through band pass filter, here we get nothing but we get the equivalent amplitude modulated signal. So once we get that amplitude modulated signal, okay, or AM signal, then we can use envelope detector to detect the envelope of the original information signal. Fine. So we get the envelope for 0 from band pass filter 2, we get envelope for corresponding to 1 from this. Okay, and then depending on whichever bit we are detecting, we'll be using a comparator where we compare our data with a threshold, and we will generate the output bits ones and zeros depending on my FSK signal. Okay, so I hope this thing is pretty clear to all of you, that how does non-coherent binary FSK detection works. Fine. Next. So this envelope detector is nothing but you have diode and your low pass filter, which acts as your envelope detector. So next we have coherent binary FSK detection. So here we'll be using a locally generated carrier, and obviously we will be multiplying this locally generated carrier with my FSK signal. And when we multiply two frequencies, we already know that we will have some frequencies and difference frequencies. Okay, and then when we pass those frequencies through appropriate filters, we can get our original signal. So you can see these are the locally generated carrier frequencies. Since there are two frequencies, so we have two oscillators. Okay, and it is because of these carrier oscillators present at the receiver side, we call it as coherent binary FSK detection. So this is the binary FSK signal. We know that balance modulator, what it does, it works like a multiplier. Okay, so it multiplies my carrier frequency with my FSK signal in the balance modulator 1. Okay, and in the balance modulator 2, my FSK signal is multiplied with second carrier frequency. Okay, so your balance modulator 1 will give output corresponding to one frequency F1. BM2 will give output corresponding to frequency F2. Okay, and if you carefully see, these are nothing but the integrators, and I told you integrators are nothing but my low pass filter. Okay, so the output of these balance modulators will be passed through a low pass filter. Okay, and then these outputs will be subtracted. I'll just show you how do we get those things mathematically, and then that output will be compared with a threshold, predetermined threshold, and we will decide whether 1 has been received or 0 has been received. Fine, so let us see that thing mathematically. So we have two synchronous carriers. See, this is what I was trying to point out, that these carriers both this carrier in balance modulator 1 and carrier in balance modulator 2, these need to be synchronous. Their phase must be matched. So I am assuming that my carriers are already synchronized. Okay, so these carriers are represented by small vc1 and small vc2. Fine, so here in this mathematical analysis, I'll be explaining how does this upper part of this detector work. The lower part works in exactly same fashion as the upper part. So you can correlate the working of upper part with the lower part. So you see here that the output of multiplier in the upper channel. So obviously we have two frequencies present. Fine, one is F1 and F2. Your BFSK signal is continuously present in both the branches for the entire duration. Okay, so we will consider both things. So for the upper channel, I'll be considering the frequency during 1 as well as the frequency during 0 also. Okay, because I'll be coming across two frequencies, both frequencies in each of the branches. So you can see here the output of the multiplier in upper channel. Okay, during the interval when we have frequency omega 1, say this frequency. So what do we get? Obviously your balance modulator will multiply FSK signal with the carrier. Fine, so again same thing is happening during this. My frequency, original frequency is also F1, my carrier frequency is also F1. So since these two frequencies are same, so that's why I'll have cosine of omega square. Okay, and if you manipulate that thing trigonometrically, this is what you get, exactly in the same way as it was done in your ASK demodulation. Okay, so this is the output of the multiplier for F1 frequency. Then subsequently we get F2 frequency. at the input from FSK signal. Okay, so when F2 comes here from FSK, your carrier oscillator is generating F1 only. Okay, so your F1 and F2 frequencies will be multiplied, so we get some frequencies and difference frequency. So you can see that the output of the multiplier, okay, so your output of the multiplier in the upper channel during the interval frequency F2, so what happens, you get the difference frequency and the sum frequency. Okay, and when you pass this through low pass filter, you can see this twice of omega, it is a high frequency component, this is also high frequency component, this is also high frequency component, we have this as the lowest frequency component. So if you pass it through a low pass filter, you get the output which is proportional to your modulating signal. Okay, so your filter output in the upper channel is proportional to the modulating signal. Okay, so see here, when F1 came through FSK signal, your S1U is present, means your output is present. When F2 comes through FSK signal and your carrier is generating, means during this period, your output is zero. Output of low pass filter is zero because both these frequencies are higher frequencies. Okay, it means your upper branch will be giving you output only corresponding to F1. Okay, similarly your lower branch will give you output corresponding to F2. Okay, so this is how you finally are able to get the final demodulated signal, which you can compare with your threshold, and you get the output data or detected data for coherent binary FSK detection. Okay, so that's all about your FSK demodulation. As I told you, that your FSK demodulation, or sorry, FSK signal has constant amplitude, only the frequency is changing. So that's why the noise immunity of FSK signal is better as compared to ASK, because information is present in frequency change, not in the amplitude change. Okay, so that's all about your ASK and FSK. Fine. So we will talk about phase shift keying in the next class. Okay, thank you.